Hello, and a very warm welcome to this latest episode of Venena Mundi. In the previous video, we saw how people might be exposed to toxic substances as they go about their daily business. However, exposure by itself is not enough for a poison or a toxin to work. For that to happen, the substance must first get inside the body. In other words, it must be absorbed. But where and how does this happen? What makes one poison better absorbed than another? And is absorption the only way that a harmful substance can damage the body? To find out, please continue watching this episode of Venena Mundi. The chemical character of a substance is rarely enough by itself to make it harm a living organism. Even something that looks like it might be dangerous can actually turn out to be fairly harmless if it can't get into the body. Let's look at the metal barium, for example. Nearly all its compounds, like barium chloride, are highly toxic. That's because whilst in the body, barium mimics another element, potassium, which plays a key role in the function of the heart and other muscles. Once barium starts to disrupt potassium's normal activity, the result can be a dangerously irregular heartbeat and severe muscle weakness, which can prevent a person from moving, or more seriously, from breathing. So we might expect barium sulfate to be the same. Surprisingly, however, large amounts of it can be ingested without any ill effects whatsoever. You may wonder why. Well, it's because barium sulfate is so poor at entering the body that hardly any of it gets in. In fact, barium sulfate is routinely given to patients as a contrast medium for X-raying the stomach and the intestinal tract. Conversely, something else which may otherwise look chemically harmless can turn out to be deadly, especially if large enough amounts can enter the body in one go. A good example of this is common salt, sodium chloride. Whereas in normal circumstances the substance is absolutely vital for life and is considered mostly harmless, even eating a teaspoon of salt in one sitting can lead to seizures and coma. In fact, death can occur rapidly if medical help isn't given immediately. This presents us with a fundamentally important question. If getting into the body plays such a key role in poisoning and toxicity, what determines how well this happens or not? In practice, there are two leading factors: the physical state of the substance and how easily it dissolves, especially in water, but also in fats and oils. Let's start with the physical state. In practice, this largely determines the route by which a substance gets inside the body in the first place. Starting with solids, these, for the most part, are simply blocked by the skin, acting as a physical barrier. Particles are just too big to get through. Of course, solids can be swallowed, but then the wall of the digestive tract acts in a very similar way. Although not as good as skin, it still presents a pretty good barrier for keeping most solids out. Liquids, on the other hand, find it easier to get through because they have the ability to flow and can therefore seep through any gaps. In practice, no natural barrier is perfectly impervious. The skin, for example, whilst appearing to be an unbroken sheet, is in fact riddled with microscopic pores such as hair follicles and sweat glands, which largely keep most solids out, but allow liquids to go through. However, even then, the liquids may go no further, which means little or no toxicity. Both solids and liquids, of course, can also be inhaled, but this is relatively uncommon. In order to do so, they first have to break up into tiny particles, which can remain suspended in the air long enough to be breathed in. Solids are therefore normally inhaled as powders, dust and smoke, whereas liquids typically turn into mist and haze. Unfortunately, the walls of the lungs are very thin and designed to easily let gases through, which means that they're not very effective at keeping liquids and solids out either. Luckily, they and the rest of the respiratory system have some other backup defences. Namely, the walls of the airways are coated with sticky secretions, which trap most inhaled solid particles or liquid aerosols on their way down, which are then coughed up. Finally, let's turn to gases. There are very few circumstances where exposure occurs in a way that leads to absorption into the body through the skin or the digestive system. Instead, they are nearly always inhaled. Once in the lungs, they easily pass through the thin barrier which is specifically designed to let gases through easily in the first place. That's because the whole purpose of the lungs is to maximize the efficient exchange of oxygen and carbon dioxide between the blood and the surrounding air. Unfortunately, this means that other gases pass through easily as well, which is why so many are so toxic and act so rapidly. Even those which are normally considered non-toxic, like nitrogen, can become harmful in some circumstances. Consider the affliction some divers experience called the bends. It is a potentially lethal condition caused by diving below a certain depth and then rising to the surface too quickly. It happens because breathing high pressure air at depth forces excess nitrogen through the walls of the lungs into the blood. Fortunately, by itself this is not too much of a problem if certain precautions are taken. This typically involves returning back to the surface in stages, taking time at each stage for the excess nitrogen to leave the blood and be exhaled. But if the ascent to the surface is too quick, this nitrogen doesn't have enough time to pass through the walls of the lungs back into the exhaled air. Instead, the rapidly dropping water pressure allows the high concentration of nitrogen to expand and form bubbles. These can block small blood vessels, and if these happen to be in the head, they may starve the brain of oxygen, leading first to delirium and then frequently to death if left untreated. Okay, so we have just seen how the physical state of substances largely determines the route by which they enter the body. However, this is only part of the story. Another key factor that determines toxicity is the solubility of the substance in water, and to a lesser extent in fat and oil. That's because almost all the vital processes which take place in the body do so in solution. Why is that? Before we get to the answer, bear in mind that all the processes in the body involve chemical reactions of one type or another. For example, respiration consists of breaking down sugar molecules like glucose in the presence of oxygen to form carbon dioxide, water and energy, the latter being used by the body as fuel. In order for such a chemical reaction to happen, however, the individual atoms, molecules or ions must come close enough to each other, and such proximity between two solids, which are not dispersed at the atomic, molecular or ionic level, do not occur at a significant rate, so no reaction will take place. The same is true of two liquids if they're immiscible with each other. The molecules of the respective liquids just stay apart and very little will happen. By but dissolving and forming a solution, the atoms and molecules of both solids and liquids are now able to come close together and therefore to react with each other. It consequently follows that the more soluble a substance is in a solvent like water, the more of it will be able to react, and therefore generally, the more soluble a poison is, the more toxic it's likely to be. Let's now return to the example of barium sulfate. The reason why it's so safe is that it's almost totally insoluble in water. It therefore has no chance of disrupting vital reactions or processes in the body. Other barium salts, on the other hand, are more soluble, which means that the metal can get inside and exert its toxic effects. Of course, in the case of solids, by dissolving in water, it also becomes much easier for them to cross physical barriers like skin or the digestive tract, because when dissolved, they're able to seep through any pores or gaps in their surface. This is exactly the same for certain liquids, whose high density or viscosity can also make the passage through a barrier difficult, for example pitch or tar residues. In both cases, the more soluble the solid or liquid, the more of it can dissolve in a given volume of solvent like water, and therefore the more can pass through a given barrier. So there we have it. The toxicity of a substance depends not only on its chemical character, but also equally on its physical form and solubility. This, of course, is only part of the story. Once inside the body, the toxicity also very much depends on several other key factors, including which vital processes the toxin affects, as well as the body's ability to neutralize the poison and get rid of it. All these will be described in future episodes. Meanwhile, the official term used to describe a toxin's or chemical's entry into the body, organ or individual cell is absorption. We will look more closely at the mechanisms of absorption in later episodes, especially how absorption happens in those organs most often exposed to toxins like the skin, the digestive system and the lungs. Now, before ending this episode, it's important to mention that it's not always necessary for a substance to be fully or even partially absorbed for it to cause serious damage. Some substances are so chemically reactive that they don't even get a chance to pass through a barrier, but just attack and destroy it and any neighbouring tissue. Such substances are irritant, corrosive or caustic, or all at the same time. Solids and liquids can both behave this way. Common household examples include dishwasher descalers containing lactic acid, oven cleaners containing sodium hydroxide, household cleaning agents containing sodium hypochlorite, and car batteries filled with sulfuric acid. All are very widely available in the home and can cause very serious, often permanent damage to skin, eyes or the mouth, esophagus and stomach if they come into contact with these parts of the body. Many gases too can cause severe irritation. Ozone, sulfur dioxide and nitrogen oxides, for example, are all common products of industrial activity which seriously damage the respiratory system, especially the lungs. These can lead to severe bronchitis if exposure continues over an extended period of time. Other substances, whilst not causing immediate damage, may still cause subtle effects such as an allergic reaction. Skin sensitization, for example, can be caused by nickel in jewellery or by the constituents of some washing powders, particularly those labelled as biological, which contain potent enzymes to digest dirt. When inflammation follows, the resulting contact dermatitis can be a very serious and disfiguring condition. It's actually one of the most common industrial diseases. Fortunately, most corrosive or irritant substances act quickly and cause so much pain that people notice immediately and stop touching or consuming the offending substance if they can. The difference for many toxins and poisons, however, is that many initially have very few effects on the skin, lungs or the digestive system when they initially come into contact. Instead, they're absorbed and pass through unnoticed, and having done so, they move to other susceptible parts of the body where they do their damage. Okay, we've reached the end of this episode. Thank you for watching. If you liked it, please give it a thumbs up and use the comments below to say what you thought or what you'd like to see in the future. Next time, we'll look at substances, poisons and toxins that specifically enter the body through ingestion. In other words, by being eaten or drunk and subsequently swallowed. In the meantime, please don't forget to subscribe so I don't get lonely, and please click on the notification bell to make sure you don't miss the next episode. Bye for now, and see you next time.